All right then. So we should be recording right now. All the best. Anyhow, hello and welcome to the second lecture on for discrete mathematics and computing. So today we're going to be talking about expressions. Yesterday we talked about the previous lecture. We talked about what a calculational proof is, and so before we get to that, we need to dissect its parts, its constituent parts. So we're going to talk about today what terms are, what expressions are, how to combine them, and then from there get to the structure of a calculational proof. So this is very similar to linguistics, right? So let's start off from there. Okay, so everyone should be seeing my screen. If you can't, please let me know. Okay, so consider this sentence right here. Square roots do not exist for negative integers. All right, so if any of you have taken linguistics, I think it's 1L03 or 1LL3, right, in first year, you will have seen these kind of trees before, known as parse trees, right? So we have a sentence called, we have a sentence right here, square roots do not exist for negative integers. And this is a sentence, okay? And it starts off with a noun phrase, which consists of a noun, that is the square root, and another noun, that's the word root. Then a verb phrase consisting of two verbal clauses, all right? Do not, followed by exist, okay? And, sorry, somebody needs to be admitted, okay? And then finally, yet another verbal phrase, okay? So this is also known as grammatical analysis, and we're not going to do a lot of it, but it's important to understand the structure. So you have a linear sentence, square roots do not exist for negative integers, and you can turn it into a tree, okay? So let's see how we can do the same thing for mathematical expressions as well. Just before we move on, I would like to remind you that discrete mathematics with applications 1 is technically two different classes. There are two cores, and we're going to try to make them similar, but core 1 is taught by Wolfram Call, and if you're listening to my lecture, you should not be emailing Dr. Call. You should be emailing me if you need something, all right? So email me if you need something, not Dr. Call. I am technically your instructor, and he's the instructor for the other core. So please keep that in mind. Okay. Some of you in tutorial the other day went over the outline, and we talked about it in last lecture. So I would like to remind you, it has a lot of useful information, in particular a rough guideline of how we're going to be moving forwards. But there's also some new addition we made, and some of you may have forgotten about this part right here, about plagiarism. Oh, sorry, it's hard to circle with this tool. Okay. So here, let me zoom into the next one. Okay. So it can be tempting to copy paste solutions, but if it's not your own work, we will have to there will be academic penalties if it's not your own work. So we do look at the submitted solutions from time to time, and when there are exceedingly similar calculations, we make note of the persons involved, and then we might contact you. So academic dishonesty has unfortunately happened before because of the electronic nature of CalcCheck. It's very easy for people to copy paste and put things onto Facebook forums or Messenger or WhatsApp, and that is unfortunate. It does happen, and if we find out that you've been involved, there will be unfortunate consequences. So hopefully we won't need to get into that. So let's get back to today's topic at hand. We're talking about expressions. So again, like a language, but for mathematics. And hopefully we'll get to Boolean operators, which is a central topic of this class, all right? And for further adventures in computing and software. So here is a common problem that elementary textbooks to programming might specify. How do you find an integer approximation to a number, to the square root of a number? Okay. So you don't have access to the actual square root operation. So you want to look at integers. They have to be non-negative. Otherwise, you're dealing with complex numbers, and we're going to avoid that. All right. So, of course, we require a precondition on the problem. But the interesting part is, what does it mean to say it's an approximation? If I give you the number n being 9, the square root of 9 is 3. If I give you the number 16, the square root of 16 is 4. But what if I give you the square root of, if I ask for the square root of 12? 12 is not a perfect number, so it won't have an integer as a square root. But the problem asks for an integer output. Okay, we want an integer output b such that it approximates the square root of 12. Well, what we can say is we can approximate it by saying b is going to be the best integer that when you square it is going to be at most n. And then if you look at the number right after b, so b plus 1, and you square that one, it will be too big. Okay? So for example, if I ask for the square root of 12, I can say this is 3, right? Because the square of 3 is 9, and 9 is definitely less than the square of the number after 3, right? The number after 3 is 4, and the square of 4 is 16. So 16 is an overshoot, and 9 is just a little bit below, and so we approximate it this way, right? And so that's what it means when we say an integer approximation, right? So for as this example shows, 42 is an approximation, but it can be too big, all right? So we want reasonable approximations, and that's what we specify as a candidate, all right? So b such that it squares at most n, and the number after it is too big, is bigger than n. But of course, there are other ways to approximate this using, for example, the absolute function. But I personally like the b and the number after it. Of course, you can speak about the number b and the number before it, right? So there are multiple ways to specify solutions to problems, right? And just as we did before with the English setting, we can perform some grammatical analysis, right? So square roots do not exist, right, for negative integers. Again, we have a main sentence, square roots. We have some verbal clauses, verbal phrases, and some noun phrases, right? So if you're interested in this kind of stuff, you can see more of it in linguistics, and you'll see more of it in computer science, actually. So lots of fun stuff. And but what does it actually mean when we're saying we're doing grammatical analysis here, right? So how do the pieces put together? In English, it would be silly to say apple the he. You say he ate the apple, right? So you have the subject, right? You have the object, and you have the verb, right? Likewise, in mathematical formulae, the way you can organize them has a particular order, right? And so what we're going to do is we're going to discuss in particular types and how they're involved with expressions. So today we'll just start off with expressions and move on from there, okay? So this one that I mentioned earlier about a number b such that it squares at most n, and then the one after it is at least n, right? It's square. We can think of our expression, instead of a sentence, we have an expression, call it e. It's conjunctual. It's a conjunctual sequence. So we have b squared is at most n, and n squared is at most b plus 1 squared. Right? So that's what it means to say conjunctional. It's two pieces. Now, it's made of two pieces. The first piece is this infix operation, b squared, right? At most n, okay? And then the second conjunction is the other inclusion, right? Okay. So this is what it means to say it's conjunctional. So notice, this is an interesting thing. The top part right here, right, is a string, right? It's a sequence of letters, right? A sequence of symbols, b superscript 2 less than or equal to n less than or equal to parentheses b plus 1 close parentheses superscript 2. It's a linear sequence. Whereas down here, the lower part of the screen is a tree, right? There's multiple branches coming from the top node, right? So it's interesting to see that that we can read strings, right, or linear sequences as if they were trees. And we'll get back to the precise nature between precise relationship between trees and sequences later in the class. But for now, it's important to note that if you have a string, how many trees are related to it, right? And so this is the idea of a syntax, right? So we say we define an expression, right, for these sequences that we're interested in, and then we'll discuss what trees correspond to them, because a tree gives us a way to read the expression, whether it's conjunctional or associative, for example, like equals or equivales, the triple equal symbol you saw from last time. So a constant or a variable, we're going to call those expressions. If you have an expression, then putting parentheses around it is an expression. If you have a unary operator like subtraction, but for a single number, so unary inverse or negation, then you can say like -5 is also an expression. Okay. If you have a binary operation, so binary takes 2, unary takes 1, right? If you have a binary operation and you stick 2 expressions together using it, then you have another expression, right? And this is again similar to trees. If you have a unary operation, this is a tree with 1 branch. If you have a binary operation, it's a tree with 2 branches. And if you have general function application, you can have n many branches. Okay, so you can look at that in the abridged lecture notes if you like. Sorry, let's go to the next slide. Look at the trees. So again, here's our expression. We can phrase it into trees, right? So as you saw before, we can build it up slowly. Okay, so at the very first, we said this is conjunctional. So it's an abbreviation for an AND operation, right? The AND operation takes 2 sub-expressions, right? So it has 2 children trees, right? And likewise, the right child, there are 2 trees. Okay. I need better software for drawing on my screen. Apologies about that. Anyhow, go to the next slide. My software seems to be a bit slow. Okay. So let's. So as we said earlier, these are strings, right, that correspond to the linguistic sentences we saw before, and in particular, this is known as an inductive data type, right? That is to say, an expression is any one of these 4 clauses and only one of these 4 clauses, right? This is what that phrase means. We'll get to induction later on in a more precise nature, but for now, we just want to have enough to talk about it. Okay. Some of you may have seen this before as a concrete syntax because it involves, for example, parentheses, and infix operators go in the middle of an expression and prefix operator go in the front. But some of you may have heard the phrase abstract syntax trees, right? So for example, 2 times 3 plus 4 is written in a concrete syntax because it uses a language that you're comfortable with infix operators written in the middle, right? But if we look at the associated tree, right? So here's just how we generated it using the rules. But let me just get to the tree. So here's the tree associated with it, right? So notice the tree and the linear phrasing 2 times 3 plus 4 are radically different, right? 2 times 3 plus 4, we think of it as 2 times 3, right, plus 4, right? Sorry about that. However, the tree communicates more information. It tells us specifically that we're doing 2 times 3 in one branch, right, in the left branch of the infix operation, and we're doing 4 in the right branch, okay? Whereas the linear operation, we could have read it like this. We could read it as 2 times 3 plus 4. Right? There's no reason to stop us from reading it this way. Why don't we read it as 2 times 3 plus 4? And then the value of this expression would be 14, right? So is the value of this expression 14 or is the value 10, right? Is it 6 plus 4, or is it 2 times 7, right? So the linear sequences give us a nice compact way to write things down, but they're ambiguous. How do I read it? Whereas a tree is not ambiguous. A tree tells you specifically what the intended meaning is. That is to say, a single expression can have multiple trees. Okay, so let's look at a few more. Okay, so here's the other one I mentioned. We could read it as 2 times 3 plus 4. Right? Which one is which? Right? The convention that decides we should do multiplication before addition is called a precedence rule. All right, and if we don't use such conventions, then we have to put in parentheses like this. Right? But putting in parentheses can make things very hard to read, right? So the point of a precedence rule or a convention for parenthesization is to omit such parentheses and make things easier to read. Okay, so we're going to be using extensive use of precedence rules, and you've seen them most likely throughout grade school in the forms of bedmass, right? Brackets, exponents, division, multiplication, right? So likewise, we will use a similar convention, but for some new operators you might have not seen, it's important to introduce a precedence rule for them. Okay, so it's important to know what that is, and that's why we're talking about it right now. Okay, ducks. So let's look at a few more examples. All right. After we look at this list, so this table of precedences can be found in the front cover of your book. And what it means, for example, as I mentioned a moment ago regarding like bedmess, whenever you see a multiplication in an expression, you should parenthesize the multiplication or do that first, then you do an addition. Okay, so right there. Okay, so things at the very top are the things that get parentheses first, or you do them first, and things at the bottom you do last or have parentheses last. Okay, so this is the table of precedences we're going to use. So some of these symbols you haven't seen before, and that's okay. We're going to get to them one bit at a time, so it's no concern. There's also this concern about association, right? And that means if you see a symbol such as 2, it's hard to draw. I have an example later. If you get to something like 2 times 3 times 4, is that 2 times 3 times 4 or 2 times 3 times 4, right? Which one is it? For multiplication, they're the same. But for other operations like implication, right, the order matters. Which way you parenthesize a repeated chain of an operator matters. And that's called association, right? Is it left associating, right associating, right? So let's look at this a bit more. So here's a few more examples of expressions, just to be more familiar. So the first one, 5 minus 6 plus 7, right? This is an expression, and it has 2 parse trees, as we talked about before. 5 minus 6 plus 7, or 5 minus 6 plus 7, right? Here is another one. So a plus b minus c, these are variables. Instead of 5, 6, 7, we have a, b, c. And again, they can be parsed in 2 ways, right? Left branching or right branching, right? And which one is the intended one is what we get by using a convention for parenthesization. That is to say, precedence rules, okay? So, and as we said earlier, the notion of association means which way do we parenthesize a repeated operation, right? So for addition and multiplication, these are the same. Likewise for and or, and likewise for equivalence. But some operations like subtraction, exponentiation, implication do not associate. And so sometimes, depending on the convention, we might want them to associate to the left or associate to the right. So because of the cultural convention, subtraction almost always means to the left. In contrast, we're going to use implication in this class, and implication associates to the right. Right? If you remember from high school, exponentiation also associates to the right. And remember, we talked about the Curry-Howard correspondence the other day? There's a very, very intimate relationship between exponentiation and implication. In a sufficient setting, if you zoom out really out, they become essentially the same thing. So that's a really interesting thing. Yeah. But we won't get to it in this class. It's just a lot of fun stuff. In this class, we're going to use double asterisks to denote exponentiation as well. In particular, because superscripts do not. So we're defining everything in a mechanized system, and an exponentiation operation takes two arguments. By convention, we write it as a superscript, but we're not going to hard code all possible numbers that way. So we're just going to use ** in our system for exponentiation. Okay, and as usual, it associates to the right. All right. So when you're not sure about association, you can just write it in yourself. But at write in the parentheses yourself. But at one point, it will become too daunting to have so many parentheses everywhere, and so you will slowly pick up the precedence rules. So don't worry too much about it if you're not comfortable right now. But it's important to remember. And as seen in the previous slide and mentioned down here, in particular for us, implication, this the stick right arrow, is going to be associating to the right. Okay, so if you have P implies Q implies R, that always means P implies Q implies R. All right. So it seems that somebody has a question. Unfortunately, something is there's some technical concern on my side, and I cannot hear you. So we'll have to address questions after the fact. But definitely feel free to text message me on the Messenger app, and I will try to reply in real time if I see your texts. Okay. Again, apologies for that. Okay. So sometimes in mathematical circles, you'll hear people use the words term, formulae, factor. They all really mean expression, right? And again, expression just means sentence, mathematical sentence. Okay. But it's good to know about these other words that people tend to use. Term, expression, formulae. So they have their uses in particular places, but for our case, they're just tree structures, and they're essentially the same thing. Okay. And it's important to emphasize that a tree structure, if you say A plus B as a tree, you have a plus and then two nodes, right? That is, you have a plus followed by two children nodes instead of A and then a plus in the middle and then a B. So this is addressed more in the abridged lecture notes that I'll link to afterwards. Whereas a concrete syntax is one that you write in day-to-day life to make your life easier. Concrete syntax puts infix operations in the middle, okay, instead of having them at the very front for trees. And it has parentheses to help with precedence, right? This is a key difference. Trees don't have parentheses, right? Because they don't need them, right? It's built into the structure of the trees, right? Which branch dictates how things are supposed to be parenthesized. Expressions don't have branches, and so they use parentheses to mimic that, okay? So just some fun little stuff. Anyhow, it's not that big of a concern, the difference between the two. So, but it's fun stuff if you're interested in programming languages. Anyhow, whew. Let's. I would like to take questions at this point, but unfortunately, that because of technical concerns, that won't happen. So let's keep going, and hopefully, I haven't tired you out. So there are a lot of numbers. I want to tell you about all the numbers, but it would take me an infinite amount of time to tell you about all the numbers. There's 0, there's 1, there's 2, there's 3. oh boy, for every number n, there's n plus 1, right? So there's a lot of numbers. And in contrast, there's only two Booleans, true and false, right? So it's much easier to work with Booleans. In some other places, Booleans are referred to as 0 and 1, high and low, right? Up and down. I was just thinking that, sorry. We use a double stroke B to denote Booleans. In math, you've probably seen a double stroke N or for the natural numbers, or a double stroke Z for the integers, or a double stroke R for the real numbers. Okay. So for example, an equality is a Boolean. X equals 1. Is that true? Is it false? So in particular, equality is always from a type T. An equality always takes two values of a type T and returns a Boolean. All right. Other operations are, for example, negation, right? Conjunction, disjunction, implication, equivalence. Right? So for natural numbers, to define addition is really difficult. As children, you don't really learn addition. What you do is you learn addition tables, right? You have, just as you learn multiplication tables, you have addition tables. And because it's really hard to explain what two numbers add up to, and so you learn sets of them and you memorize those as a children. In contrast, the operations on Booleans, there's only two Booleans. So for example, and takes two arguments, right? The operation and takes two arguments. And so there's a table, it's a 2 by 2 table to understand how it works. So the multiplication table for and has 4 entries. Really easy. So if you if you think working with natural numbers is really easy and you've been doing that your whole life, most of this is going to be very easy stuff for you. So there's, hopefully that will bring you some comfort, right? It's really easy to memorize these tables. And some people like to think of true as 1 and false as 0, and then and they like to think of it as multiplication. And then it's really easy. Anything times 0 is 0, anything times 1 is itself. And so you're done. So these last two operators we'll get to in a little bit later. But again, this triple line equality is just equals on the Booleans, right? So equals on the Booleans can be conjunctive or associative, as we mentioned earlier. So we'll get to that in a moment. And then the last one is just its negation. All right. So the first part of this class is easy goings. So hopefully that'll make you feel comfortable for the upcoming midterm on the 22nd, I think. So again, there's the conjunctional ones and the disjunctional ones, and these ones at the very bottom have lower precedence. Right. So in particular, you're going to see a lot of formulae that have a equivales or triple line equals right in the middle, because it's the least precedence, and so you don't have to worry about parenthesization unless you're working with inequivalence at the same time. So, for example, this expression not p, because equivalence has the least precedence, we read it as not p. Okay. But now, how does not associate? Is not p not p? Well, that doesn't make sense. You can't apply a not to itself. So we say a negation is right associative, and we write it like this. Okay. So we say it's the negation of p, and so on. If you say I did not do the thing, then you did do the thing, right? So double negation. May I not play video games, right? That is to say, may I play video games, right? So double negation, right? It's like minus, right? Minus 5 is just 5, right? And so we'll prove these rules later on in the class. Just wanted to show you some of them and what they look like, right? And as I said a moment ago, notice we put the equivalence right in the middle. We've added extra space just to make it clear, but the equivalence has the lowest precedence. So on these equations, the left-hand side has parentheses and the right-hand side has parentheses, right? So these really are equations as you've seen them before. So some of you have asked questions. The recordings can't be shown in advance. The lecture is happening now in real time, so I will post the recording online. I'll send a link. Links were posted in the channel for the previous recordings as well, and you can see the recordings for this section and for the other section. So you have two different presenters to choose from, as you like. And for now, there are no slides being posted anywhere, but there are abridged lecture notes, and I will show you those at the end of the lecture. I'll show you how to get to those. I'll post a link as well. Okay, so yes, please send me more questions, and I'll try to answer them in real time if possible. Okay. So it's not important if you haven't seen these names before. It's not a big concern. You'll learn them as you go on. So this set from 336 to 342. Notice it's essentially repeated down here. These words will come up again and again in the class. Symmetry, change the order around. Associativity means it doesn't matter if you parenthesize to the right or to the left. Idempotency means you have an illusion of free will. Idempotency is that notion of free will. It's either P or P. Well, there's only one, right? So it's an illusion of free will. Zero laws means there's a black hole that sucks everything up. And the identity means there's a do nothing operation that leaves everything alone. So these are very common laws. They're very natural, and we'll get back to them in time. So there's no need to worry if you're not comfortable with it. But definitely, please bring questions. And distributivity laws, you've seen those before for addition and multiplication. So please bring questions to tutorials if you're not comfortable about anything. And, not too much of a concern. This last one, De Morgan, some of you might think it's a bit strange what's going on here with negations, but you've seen this one before too. So I'll get back to this at the end of the lecture, and I'll show you where you've seen this before. So you've seen all of these before. Again, so I'll show you that at the very end. So these are not new for you. It's just a new syntax. So I'll try to quell any concerns at the very end. Made a little comparison chart for you. So as I mentioned earlier, the binary operations, their truth tables are very easy. This is the truth table for conjunction, and, right? So this multiplication table is also called a truth table. If I'm given two things are false, right? Right here, the very first one, then their conjunction, their and, is also going to be false, right? So if the moon is green and 2 + 2 = 7, well, both of those are gibberish, so I have gibberish, right? They're both false, so the result is false. If either one of the things is false, then the whole thing is also false, right? So for example, if the moon is green and 1 + 1 = 2, well, 1 + 1 = 2 is true, but the moon is not green, so the whole expression becomes false, right? So when you're telling a truth, when you're making a statement, a propositional statement, and you tell someone this and that, then what you said is true if both pieces are true. If either one of them is false or both are false, then the whole thing is false, right? So that's the last row of the table, right? True and true is true. Everything else is false, okay? So it's really easy. This is what I was trying to communicate earlier. These tables are very easy to memorize. When is and true? Only when both of the pieces are true. Otherwise, it's not, right? So it's really easy to memorize. When is or true? Or is true when one or the other is true, right? So again, not. So I was just thinking a question. Sorry. The only time you say this or that is false is if only both pieces are false. So right now we're giving these intuitive truth tables or times tables, but the way we're going to work with them throughout the class is through their interface, right? What properties they satisfy rather than what implementations we use, right? So as I said, if you have P or Q and you want to know if P or Q is true, you just look at P. If it's false, then you look at Q, right? If P is true, then we're done. Everything is true. Okay, that's a particular implementation. Another way to define OR is to say P or Q is true if I look at Q first. If Q is true, then the whole thing is true. If Q is false, then I return P. Okay, so these are different implementations. Okay, another implementation might say check both of them regardless. Right. So these are, if you've done some programming, you might heard of these as short circuit OR operations. Right. So we're not going to focus on any particular implementation. We're going to work with an interface of the properties that OR should satisfy. Okay. And if you're not a computer person, you don't do a lot of programming, there's no concern, right? We'll talk about these natural properties as we get to them, so it's not a concern. Okay. So again, there's only two values, true and false. We denote it by a double stroke B, right? The equality for them is known as equivalence, and it's written with 3 lines, right? We can read it as equivales, is equivalent to, as if and only if, as precisely when, as exactly when, and some people will actually just say equals, right? Because it is just equality on the Booleans, right? So false is equal to false, that's true, right? False is equal to true, that's never true, right? So the only time that two things are equal is when they're the same thing, right? So we'll talk about notions of equality more in class. Equality is a very slippery subject. There is a fun little paper called "When is one thing equal to another thing?" If you have the inclination, I recommend reading it. It's a fun little paper. But yes, equality is a slippery subject. So again, we're going to work with equality as we would work with the other operators using an interface rather than a particular implementation. All right. So for us, two things are equal precisely when those two things are actually the same one thing. Okay. So some people will say it's just reflexivity, right? And we will get to that rule as well, right? So no concern. So as I mentioned earlier, we have an equals written with 2 parallel lines, as you've seen before, and an equivales written with 3 parallel lines. And the difference between the two is that we treat the first one, the equals, as a conjunctional. P equals Q equals R means P equals Q and Q equals R. Whereas equivalence, we treat it associatively. P equivales Q equivales R means parenthesized to the left or parenthesized to the right. There's no and. Okay, so let's get to that in a moment. Make sure I'm not running out over time. So a conjunctional operator, right, means there's actually an and in there. And almost everything you've seen in grade school, whenever you have a chain of relational operators, that chain of relations means there's a bunch of ands in there. Okay, so less than followed by an equal followed by an at most usually means this and that and this and that. And by the convention in the book and in the previous slide, and has the least precedence. So we parenthesize this way. And again, this is with any infix relational operator. So we'll get to those later on in the class, but I just want to show you some more examples. So here's less than 5 and a membership of S and a subset or contained in T. Again, if you're not if you haven't seen the symbols before, it's no big concern, right? That's completely fine. I'm just trying to show you examples of this idea. So this is what it means to say conjunctional, and the book also makes use of this. So definitely please consider reading chapter 2 of the book. Okay. So now that we've talked about the majority of the required pieces, we can actually get back to what we said at the very beginning, right? An expression is like a sentence, right? And a expressions or subterms, if you will, are like the words in the sentence, okay? And the variables and the constants are like the names, right? Or pronouns in a sentence, all right? Then a proof is like a paragraph, okay? It's like a paragraph or like a story, right? So we write the very beginning of our story. We start off with E0, and then we slowly and gently guide the reader to E1, E2, E3, and then this shows that E0 equals E3, okay? So if you've ever read a story, it can be very botchy if there's no transition sentences, right? How did new characters come into play? What's the relationship between the characters? How do they fit in, right? What are you going to tell the reader explicitly versus what do you expect the reader to know? If your story is very terse, it might not be fun to read. People might read it because they have to, or but they might not enjoy reading it. And if they don't enjoy reading it, maybe they don't want to talk to you anymore, right? So you want to have some transitions in your story to make it more accessible. And in our setting, these transitions are in the form of calculational steps or calculational hints. Between every two steps, we explain why this is the case, what's going on. It's a communication from the writer to the reader, right? This serves to, as a writer, you're actually convincing me you know what's going on. And as a reader, I'm being told what's going on and I don't have to think, what's going on? I have to solve this puzzle. So explanations are helpful both for the reader and for the writer. They communicate to the reader that you know what you're doing, right? You gave me a good explanation. You clearly know what you're doing. Good job. And me, I'm reading it. I can be like, this is what he's doing. I understand, right? Oh no, she maybe made a mistake, but she put a comment, right? So you can put comments in there, explain what's going on, and they don't have to be a single line, as you'll see in a moment or two. They can be multiple line hints explaining what's going on. So I'll get to that in a moment. All right. All right. So this is conjunctional, as I said a moment ago. It's easy. So we read it as the propositions in between. We forget about the transitions, right? To understand the meaning of a phrase, of the phrase, and we realize, hey, wait a minute. Every step, right? If you ignore the hint, gives you an equality. So E0 equals E1, and E1 equals E2, and E2 equals E3. And then because equality is transitive, that is, you can glue all the common pieces together, we get E0 is equal to E3, all right? So you can glue these two pieces together, right? The E1s, and you can glue the E2s together, right? And then you're left with E0 to E3. So we'll get to transitive relations later on in the class, and besides having just equalities on the side, you can have other transitive operations, and we'll get to see more of those in the class. We're a bit short on time, so I'm going to stop here, and I'm just going to show you where the abridged notes are, and get back to those theorems we talked about a moment ago. So let me open up an internet browser. Okay. So here is where you can find some videos for the previous lecture and our current lecture. This is just alhassy.github.io/calccheck. There's some documentation. Some of it is outdated, so I'll need to update it, but most of it should work. If you find any mistakes or typos, please let me know and I'll fix those. Or if you're tech savvy, you can make a pull request. So this is just a standard read the docs, right? It covers a lot of stuff that you won't need to know for a long time. There's also examples here about Alice and Puzzle Land and Mad Hatters and things, and you can formalize them and practice with them if you're interested. So I just wanted to let you know that there is further resources for you. And then there's some abridged lecture notes. So I got a few texts about students wanting explicit slides. So for now, we're going to try just the abridged lecture notes. We found in the past that when slides are available, students tend to not read the book and heavily depend on learning everything from the slides, which is not appropriate. There's a lot of content that you won't get just by reading from the slides. Okay. So here is what I mentioned earlier about Boolean laws and numeric laws. So let me show you that in a moment. So let me just zoom in. All right. So I tried to say that you've seen these laws before, that they're not new to you. Okay. So let me just show you a few of them. So this down arrow is what the book uses for minimum, right? The smaller of two numbers. Okay. And now all of these strange looking laws are suddenly very familiar, right? If I try to find the minimum of two numbers, m and n, that's the same thing as the minimum of n and m, right? If I'm finding the minimum of a number n itself, that's just the minimum of that number. If I try to find the minimum of a number and infinity, that's always going to be infinity. Every number is smaller than positive infinity. And this is a typo. I'll fix this. It should be negative infinity. Right? But many of the laws you're very familiar with suddenly have counterparts in arithmetic. So for example, De Morgan can be thought of as, if I find the additive inverse or subtraction of a minimum, I get a maximum. And if I negate a maximum, I get a minimum. Right? So a bunch of the laws can be thought of in this more familiar setting. And again, if you remember, I said, if you think of and like multiplication or like minimum, then suddenly almost all the rules have a numeric counterpart. So I hope that helps. So these are the abridged slides. So they contain some stuff we talked about today about expression trees and what these operations are. So this is what we're thinking of doing for now. And as I mentioned a moment ago, if a proof is telling a story. So here's a story, and this story is very terse. It's 3 lines long. Okay, being short isn't always a problem. But for example, it introduces names really tersely. Say this thing, right? So it can be a bit tough to follow. A calculational proof, in contrast, is a bit longer. But everything, like for example, this notation is introduced right in the middle. In this example only, we're using a vertical bar, but in CalCheck and in the notebook, we'll use a left angle and a right angle to delimit hints. Anyhow, I hope you found today's lecture not too daunting, and I hope you see that some of these ideas are not really that new. They're just in a new setting. And I wish you all the best. Goodbye.